Traversal using relays around NAT turn. Traversal using relays around NAT turn provides a way for two or more systems to communicate even if they are located behind relatively uncooperative NATs. As a last resort method to support communication in such circumstances, it involves a relay server that shuttles data between systems that could otherwise not communicate. Using extensions to stun and some turn-specific messages, it supports communication even when most other approaches have failed, provided a common server that is not behind a NAT can be reached by each client. If all NATs were compliant with the behave specifications, turn would not be necessary. Direct communication methods, i.e., that do not use turn, are almost always preferable to using turn servers. Referring to figure 7.11, a turn client behind a NAT contacts a turn server, usually on the public internet, and indicates the other systems called peers with which it wishes to communicate. Finding the server's address and the appropriate protocol to use for communication is accomplished using a special DNS NAPTR record, see Chapter 11 and RFC 5928, or by manual configuration. The client obtains address and port information called the relay transport address from the server, which are the address and port numbers used by the turn server to communicate with the peers. The client also obtains its own server reflexive transport address. Peers also have server reflexive transport addresses that represent their external addresses. These addresses are needed by the client and server to perform the plumbing necessary to interconnect the client and its peers. The method used to exchange this addressing information is not defined within the scope of turn. Instead, this information must be exchanged using some other mechanism, i.e. ICE C section 7.4.5, in order for turn servers to be used effectively. The client used turn commands to create and maintain allocations on the server. An allocation resembles multi-way NAT binding and includes the unique relay transport address that each peer can use to reach the client. Server or peer data is sent using straightforward turn messages traditionally carried in UDP or IPv4. Enhancement support TCP, RFC 6062 and IPv6, and also relaying between IPv4 and IPv6. RFC 6156. Server or client data is encapsulated with an indication of corresponding peers that sent or should receive the associated data. The client or server connection has been specified for UDP over IPv4, TCP over IPv4, and TCP over IPv4 with TLS. Figure 7.11. Based on RFC 5766, a turn server helps clients behind bad NATs to communicate by relaying traffic. Traffic flowing between client and server may use TCP, UDP, or TCP with TLs. Traffic between the server and one or more peers uses UDP. Relaying is a last resort measure for communication. Direct methods are prepared if available. Establishing an allocation requires the client to be authenticated, usually using the STAN long-term credential mechanism. Turn supports two methods for copying data between a client and its peers. The first encodes data using STAN methods called send and data defined in RFC 5766, which are STAN indicators and therefore not authenticated. The other uses a turn-specific concept called channels, Channels are communication paths between a client and a peer that have less overhead than the send and data methods. Messages carried over channels use a smaller 4-byte header that is incompatible with larger STAN formatted messages ordinarily used by Turn. Up to 16K channels can be associated with an allocation. Channels were developed to help some applications such as VoIP that prefer to use relatively small packets to reduce latency and overhead. In operation, the client makes a request to obtain an allocation using a turn-defined STAN allocate method. If successful, the server responds with a success indicator that the allocated relayed transport address. A request might be denied if the client fails to provide adequate authentication to the server. The client must now send refresh messages to keep the allocation alive. Allocations expire in 10 minutes if not refreshed, unless the client included an alternate lifetime value encoded as a STAN lifetime attribute in the allocation request. Allocation may be deleted by requesting an allocation with 0 lifetime. When an allocation expires, so do all of its associated channels. Allocations are represented using 5-tuple. At the client, the 5-tuple includes the client host transport address and port number, server transport address and port number, and the transport protocol used to communicate with the server. At the server, the same 5-tuple is used, except the client's host transport address and port are replaced with its server reflexive address and port. An allocation may have 0 or more associated permissions to limit the patterns of connectivity that are permitted through the turn server. Each permission includes an IP address restriction such that only packets with matching source address received at the turn server have their data payloads forwarded to the corresponding client. Permissions are deleted if not refreshed within 5 minutes. Turn enhances STAN with 6 methods, 9 attributes, and 6 error response codes. These can be partitioned roughly into support for establishing and maintaining allocations, authentication, and manipulating channels. The 6 methods and their method numbers are as follows: allocate 3, refresh 4, send 6, data 7, create permission 8, and channel bind 9. The first 2 establish and keep allocations alive. Send and data use STAN messages to encapsulate data from client to server and vice versa, respectively. Create permission establishes or refreshes a permission, and channel bind associates a particular peer with a 16-bit channel number. The error messages indicate problems with turn features such as authentication failure or running out of resources, i.e. channel numbers. The 9 STAN attribute names, values, and purposes defined by turn are given in Table 7.3. Name, channel number, value 0x00000C, purpose or use indicates what channel associated data belongs to. Name, lifetime, value 0x000D, purpose or use requested allocation timeout in seconds. Name, XOR peer address, value 0x0012, purpose or use appears address and port using XOR encoding. Name, data, value 0x0013, purpose or use holds data for send or data indication. Name, XOR relayed address, value 0x0016, purpose or use server's address and port allocated for a client. Name, even port, value 0x0018, purpose or use request that the relay transport addressing information use an even port, optionally request allocation of the next port in sequence. Name requested dash transport, value 0x0019, purpose or use used in client to request that specific transport be used informing the transport address. Values are drawn from the IPv4 protocol or IPv6 next hop header field values. Name, don't fragment, value 0x001A. Request that the server set don't fragment bit in the IPv4 header in packets sent to peers. Name, reservation token, value 0x0022, unique identifier for a relay transport address held by the server. The value is provided to the client as a reference. Figure 7.12. A turn allocation request is a stun message using message type 0x0003. This request also indicates the requested transport and software attributes. It does not include authentication information. According to stun long-term credentials, this request will fail. A turn request takes the form of a stun message whose message type is an allocation request. Figure 7.12 shows an example. According to the stun long-term credential mechanism, the initial allocation request shown in Figure 7.12 did not include authentication information, so it is rejected by the server. The rejection is indicated by an allocation error response shown in Figure 7.13. The error message in Figure 7.13 provides the realm attribute via genie.ca and the nonce value the client requires to form its next request. The message also includes the message integrity attribute so the client can check that the message has not been modified and the requested realm and nonce are correct. A subsequent request includes the username, nonce, and message integrity attributes. See Figure 7.14. After receiving the request, including long-term credentials as shown in Figure 7.14, the server computes its own version of the message integrity value and compares the result against the message integrity attribute value if they match. This is sufficient information for the turn server to conclude that the client must hold the appropriate password. It then permits the allocation and indicate the result to the client. See Figure 7.15. Figure 7.13, a turn allocation error response include the error code attribute with the value 401 unauthorized. The message is integrity protected and includes the realm and nonce attributes required by the client informing another authenticated allocation request. The allocation request is successful as shown in Figure 7.15 and the relayed transport address is 216.146.46.55:49261. Note that Wireshark performs the XOR operation to display the decoded address. At this point, the client can proceed to use the turn server for relaying to peers. Once this is finished, the allocation can be removed. About 4 seconds later, packet 5 and 6 in Figure 7.15 indicate the client's request to remove the allocation. The request is expressed as a refresh with lifetime set to 0. The server responds with the success indicator and removes the allocation. Note that bandwidth attribute has been included in the allocation and refresh success indicators. This attribute, defined by a draft version of RFC 5766 but ultimately deprecated, was intended to hold the peak bandwidth in kilobytes per second permitted on the allocation. This attribute may be redefined in the future. Figure 7.14. A second turn allocation request includes the username, realm, nonce, and message integrity attributes. These are used by the server to verify integrity of the message and the identity of the client. If successful, the client server authenticates the request and performs the allocation. As suggested previously, turn has the disadvantage that traffic must be relayed through the turn server, and this can lead to inefficient routing, i.e. the turn server may be far away from a client and peer that are proximal. In addition, Certain other traffic contents are not passed through from peer to client using turn. This includes ICMP values, see Chapter 8, TTL hop limit field values, and IPDS field values. Also, a requesting turn client must implement the STAN long-term credential mechanism and have some form of login credential or account assigned by turn server operator. This helps to avoid uncontrolled use of open turn server but creates somewhat greater configuration complexity. Figure 7.15, a turn allocation success response. The message is integrity protected and includes the XOR relayed address attribute identifying the port and address allocated by the turn server. The allocation is deleted if not refreshed. Interactive Connection Establishment ICE. Given the large variety of NOTs deployed and the various mechanisms that may be necessary to traverse them, a generic facility called Interactive Connectivity Establishment ICE RFC 5245 has been developed to help UDP-based applications hosted behind the NOT establish connectivity. ICE is a set of heuristics by which an application can perform unSOP in a relatively predictable fashion. In its operation, ICE makes use of other protocols such as turn and stun. A proposal extends the use of ICE to TCP-based applications. ICE works with and extends offer or answer protocols such as the session description protocol used with Unicast SIP connection establishment RFC 3264. These protocols involve an offer of service with an accompanying set of service parameters followed by an answer that also include a set of selected options. It is increasingly common to find ICE clients incorporated into VoIP applications that use SDP or SIP for establishing communications. However, in such circumstances, ICE is used for establishing NAT traversal for media streams, such as the audio or video portion of all carried using RTP or SRTP, while another mechanism called SIP outbound handles the SIP signaling information, such as who is being called. Although in practice, ICE has been used primarily with SIP or STP based applications, it can also be used as a generic NAT traversal mechanism for other applications. One such example is the use of ICE over UDP, with Jingle defined as an extension to the core extensible messaging and presence protocol XMPP. Ordinarily, ICE works to establish communication between two SDP entities called agents by first determining a set of candidate transport addresses that each agent might use for communicating with the other. Referring to figure 7.11, these addresses could be host transport, server, reflexive, or relayed addresses. ICE may make use of both stun and turn to determine the candidate transport addresses. ICE then orders these addresses according to a priority assignment algorithm. The algorithm arranges for addresses that provide direct connectivity to receive greater priority than those that require data relaying. ICE then provides the set of prioritized addresses to its peer agent, which engages in a similar behavior. Ultimately, two agents agree on the best set of usable address pairs and indicate the selected results to the other peer. Determination of which candidate transport addresses are available is accomplished using a sequence of checks encoded as stun messages. ICE has several optimizations to decrease the latency of agreeing on the selected candidate, which are beyond the scope of this discussion. ICE begins by attempting to discover all available candidate addresses. Addresses may be locally assigned transport addresses, multiple if the agent is multi-homed, server reflexive addresses or relay addresses determined by turn. After assigning each address a priority, an agent sends the prioritized list to its peer using SDP. The peer performs the same operation, resulting in each agent having two prioritized lists. Each agent then forms an identical set of prioritized candidate pairs by pairing up the two lists. A set of checks are performed on the candidate pairs in a particular order to determine which addresses will ultimately be selected. Generally, the priority ordering prefers a candidate pairs with fewer nuts or relays. The candidate pair ultimately selected is determined by a controlling agent assigned by ICE. The controlling agent nominates which validity candidate pairs are to be used according to its order of preference. The controlling agent may try all pairs and subsequently make its choice called regular nomination, or may use the first viable pair called aggressive nomination. A nomination is expressed as a flag in a stun message referring to a particular pair. Aggressive nomination is performed by setting the nominate flag in every request. Checks are sent as stun binding request messages exchanged between the two agents using the addressing information being checked. Checks are initiated by timer or scheduled as a result of an incoming check from a peer called a triggered check. Responses arrive in the form of stun binding responses that contain addressing information. In some circumstances, this may reveal a new server reflexive address to the agent, i.e., because a different NAT is used between agents from the one that was used when the candidate addresses were first determined using stun or turn servers. Should this happen, the agent gains a new address called a peer reflexive candidate, which ICE adds to the set of candidate addresses. ICE checks are integrity checked using stun's short-term credential mechanism and use the stun fingerprint attribute. When turn is used, the ICE client uses turn permission to limit the turn binding to the remote candidate address of interest. ICE incorporates the concept of different implementations. Light implementations are designed for deployment in systems that do not employ NAT. They do not ever act as controlling agent unless interacting with another light implementation. They also do not perform the checks mentioned earlier as do fall implementations. The type of an ICE implementation is dictated in stun messages it sends. All ICE implementations must comply with stun RFC 5389, but light implementation will only ever act as stun servers. ICE extends stun with the attributes described in Table 7.4. Table 7.4 stun attributes defined by ICE: name, priority, value 0x0024, purpose or use, computed priority of associated candidate address, name, use candidate, value 0x0025, purpose or use, indicates selection of candidate by controlling agent. Name, ICE controlled, value 0x8029, purpose or use, indicates sender of message is controlled agent. Name, ICE dash controlling, value 0x8028, purpose or use, indicates sender of message is controlling agent. A check is a stun binding request containing the priority attribute. The value is equal to the value assigned by the algorithm described in section 4.1.2 of RFC 5245. The ICE controlling and ICE controlled attributes are included in stun request when the sender is the controlling or controlled agent respectively. A controlling agent may also include a use candidate attribute. If present, this attribute indicates which candidate the controlling agent wishes to select for subsequent use. So let's connect that to NAT session control flow. Let's say your client 192.168.1.10 sends a TCP connection to a server 142.251.221.14 YouTube. Client sends scene. TCP wants to start connection. It sends a scene packet. Scene flag set equal to 1. Example, SRC IP colon 192.168.1.10 SRC port colon 53000 DST IP colon 142.251.221.14 DST port colon 443. NAT router intercepts. The packet reaches your home router or converge CG NAT. The NAT sees that this internal private address 192.168.x.x isn't valid on the public internet. Third, NAT creates a session translation entry. The NAT allocates a new public source port and associates it with your internal one. Example NAT map entry. Internal 192.168.10 colon 53000 to public 123.45.67.89 colon 4001. Destination 142.251.221.14 colon 443. This entry lives in the NAT translation table in kernel memory. NAT rewrites and forwards the scene. Before sending the packet out, it rewrites the IP and port. SRC IP colon 123.45.67.89 SRC port colon 4001 DST IP colon 142.251.221.14 DST port colon 443. Then forwards the scene to the server. Server replies with scene plus ACK. The server replies to 123.45.67.89 colon 4001. NAT look up its table and finds the entry, translating back public 123.45.67.89 colon 4001 to internal 192.168.1.10 colon 53000. The NAT rewrites and forwards the packet to your internal host. 6. Client sends ACK. The client completes the three-way handshake. From then on, NAT uses the same mapping for all packets in this connection. Big picture, you're absolutely right. Clients send scene, did not create session, then NAT provides map. That's exactly the chain, and you now understand NAT's main behavior at the moment a connection begins. From there, NAT acts like a stateful translator using that map until the session closes, FIN or RST segment or times out. Bonus, where this lives, the NAT session table lives in layer 3 to 4 of your router kernel. Each entry stores source and destination IP or port, IP/port, protocol, TCP or UDP, timeout, counters, state, i.e. scene and underscore sent, comma established. In Linux, this lives in /proc/net/nf-contract and is managed by contract module. So that's a nice bit of progress tracking, both for habits and for the technical work. If you focus on the NAT part, you noted points 6 to 9. You've basically captured the sequence that happened when a client behind the NAT opens TCP session. First, a client sends a scene TCP segment with the scene flag to set to start a connection. NAT interprets it. The router sees the packet coming from a private address and knows it can forward it unchanged to the internet. NAT creates a translation entry. It records the internal IP and port and picks an external port public IP pair to represent this connection. Fourth, NAT rewrites and forwards. The packet leaving your network now has the public source address or port. Fifth, replies are translated back. When the remote server sends scene to ACK to the public address, the NAT looks up the entry and rewrites the packet so your client receives it. That entry stays in a small connection table in the router's memory until the session closes or times out. If you'd like, sorry. So great, let's tie the NAT session flow to the actual Linux pieces that create, store, and update the NAT entry, what you call the NAT map, and show concrete commands example you can run on your machine to observe. So we'll cover where the code and component leave the packet path through kernel hooks, where contract or NAT act, what a contract or NAT entry looks like, live output, TCP state and timeouts, how replies gets rewritten back to the client. First, component and where they run. Kernel filter subsystem equal packet processing framework inside the kernel. It exposes hooks where modules can expect or modify packets. Contract or NF underscore contract equal kernel module that tracks connection state. L3 or L4 tuples plus state machine. It stores the connection table, the translation or session table. NF underscore NAT equal kernel module that performs actual address or port rewrites. SNAT slash DNAT using mappings created when contracts sees a new flow. IP tables slash NF tables user space equal rules that attach NAT or forwarding policies to NET filter hooks. They don't store the session table but control when NAT is applied. Contract dash tools dash libnet filter underscore contract user space utilities contract underscore dash L and netlink interface clients to read or flash contract entries. Files or places to look on a Linux box. Kernel modules dash config nf underscore contract nf underscore contract underscore IPv4 older nf underscore contract underscore netlink nf underscore nat proc fs slash proc slash net slash nf underscore contract or slash proc slash net slash IP underscore contract on older kernels. Tools sudo apt install contract to sudo or sudo contract dash L. Net filter rules sudo IP tables dash T not dash capital L dash small n dash small b or sudo nft list rule set. Packet path high level how scene creates the mapping. Packets traverse net filter hooks simplified outgoing client flow. First, local socket to kernel IP socket. Up writes TCP builds SYN packet and hands to IP layer. 2. Or second, NF underscore init underscore pre underscore routing. Packet enters incoming hook. Not typical for locally generated. For forwarded packets, it would. For locally generated contract sees it at the output or post routing side as packet leaves. Third, contract sees the packet. The contract subsystem checks, do I have connection entry for this 5 tuple? If no, first SYN contract creates a new connection object. State SYN underscore send slash new depending on timing. It stores the tuple SRC IP, SRC port, DST IP, DST port, protocol, timestamps, and state. Fourth, NF underscore NAT performs source NAT, rewrite, SNAT. For SNAT, home router with public to with private to public, NF underscore NAT picks a public port and IP and creates the mapping tied to the contract entry. The actual rewrite is applied at post routing for source NAT, so the outgoing packet gets the public IP colon port. Fifth, packet leaves to the internet with public IP colon port. 6. Replies come back to the public IP colon port. Arrives at router. Pre-routing contract sees it, matches the contract entry, and NF underscore NAT rewrites destination back to internal IP colon port and forwards to the client. Key point, contract and NF underscore NAT cooperate. Contract provides sessions, identity, and state NF underscore NAT stores rewrite info and applies changes at the appropriate hook. Third, where the mapping is applied, pre-routing versus post-routing. SNAT source route, rewriting the source address or port applied in post-routing. Packet already selected interface to live on. Kernel rewrites just before packet leaves. DNAT, destination NAT, applied in pre-routing, incoming packet's destination, rewritten before routing decision. Fourth, example view the mapping live, install contract tools, then generate a connection and list contract entries. Commands run on your Linux router or host. Install tools, Debian or Ubuntu, sudo apt update, sudo apt install contract, list current contract entries, sudo contract dash capital L, or cat proc file raw, sudo cat slash proc slash net slash nf underscore contract vertical bar tail dash small n20. Typical contract dash capital L TCP entry looks like this. TCP 6.431998 established, SRC equals 192.168.1.10, DST equals 142.251.221.14, Sport equal 53000, dport equals 443, SRC equal 142.251.221.14, DST equal 123.45.67.89, Sport 443 equal 443, dport equal 4001, assured mark equal 0, use equal 1. Breakdown TCP 6 equal protocol 431998, timeout seconds left. Establish equal contract TCP state. SRC equal 192.168.1.10, DST equal 142.251.221.14, Sport equal 53000, dport equal 443 equal original tuple, SRC equal 142.251.221.14, DST equal 123.45.67.89, Sport equal 443, dport equal 4001 equal reply tuple as seen externally. Note public IP port. Dport equal 4001 is the public port not assigned. Proc file lines are similar but more raw. TCP states and timeouts. Contract tracks TCP state, scene underscore sent, scene underscore rec v, establish, fin underscore wait, time underscore wait, etc. Kernel has tanables, tanables, i.e. /proc /sys /net filter /nf underscore contract underscore TCP underscore timeout underscore establish /proc /sys /net filter /nf underscore contract underscore TCP underscore timeout underscore scene underscore sent. You can view or adjust this to alter how long entries stay. When contract sees a scene, it creates the entry and sets an appropriate timeout until handshake completes. When established, a longer timeout applies. How replies get rewritten? Concrete. Incoming packet to public underscore IP public underscore port. Kernel contract lookup finds the contract entry. Match on reply. Tuple 2. It knows the internal mapping. NF underscore NAT rewrites the DST IP/port back to 192.168.1.10 53000. Packet routed or forwarded to internal host. This is why the NAT table must be stateful, because replies must be correlated to the original internal host or port. Where is the code or what functions? Conceptual. The high-level flow is implemented in the kernel net filter code. C. Contract code in net/net filter. Files name nf underscore contract maintains tables and state machines. NAT code in net underscore /net filter /nf underscore NAT does allocation of ports and rewrites. User space /tools IP tables /nf tables manipulate rules. Contract state is kernel only and exposed via netlink and /proc. Number 8 examples you can run right now. Start a client connection from a laptop, curl https example.com on router, sudo contract dash capital L vertical bar grep your laptop IP, you'll see a new entry with public port mapping. Then third, sudo iptables dash multi nat dash capital L dash small n dash v shows NAT rules, SNAT, masquerade, etc. that cause translation. Extra notes or facts you had earlier. Short, where does the session table live? Kernel memory. Visible via slash proc slash net slash nf underscore contract or contract dash capital L. Who assigns public port? nf underscore nat chooses an available ephemeral port or range and writes into the contract slash nat mapping. What triggers creation? The first packet seen or TCP processed by contract and matched by NAT rules. How long does it take? Until connection close or timeouts. Configurable in proc slash sys slash net filter slash asterisk. User space involvement only for rule management. iptables slash nft contract events can be observed slash subscribe via netlinks libnet filter underscore contract. So first, what actually happens in the real world when you use the internet? First, your device to NAT to ISP to internet real world flow. When your PC starts a TCP connection, example loading YouTube, this happens. Step A, TCP handshake begins. Your PC sends SYN, SRC IP 192.168, etc., SRC port 52314, DST IP 142.251, etc., which is YouTube, DST port 443. Step B, NAT happens at your converged router. Your router creates a NAT entry. Internal 192.168.252.314. External 161.49.240.021. The example, it rewrites your SYN to SRC IP public 161.49, etc. to SRC port 40021. This is what you see in traceroute hubs 2 to 5 in the previous video in all converged addresses. Step C, your ISP routes forwards it. Each router checks destination IP, TTL, whether it should drop or forward, whether MTU is too big, might trigger PMTU discovery, whether firewall rules allows it. These are packet filter firewalls on routers. Step D, PMTU kicks in. If a router in the path cannot forward a packet larger than its MTU, it sends ICMP fragmentation needed, packet too big. Or if it's an IPv4, therefore it will fragment it in each router on the internet. Your OS kernel shrinks PMTU in layer 3 IPv4 or IPv6 stacks, stores it in PMTU cache. TCP automatically reduces MSS before sending more packets. UDP apps, games, or VoIP usually pre-design packets under 1 to 100 bytes because PMTU might vary. This is happening every day, but you don't see it unless PMTU breaks. Second, where firewalls fit in. Proxy firewalls in application layer, packet filter firewalls IP layer. In the real world, your home router runs a packet filter firewall, iptables or NF tables. It drops unsolicited inbound packets because NAT doesn't know them. Converged routers, your traceroute HAPS 3 to 7, they also run packet filter firewalls. It drop unwanted traffic, read limit ICMP, maybe drop PMTU packets, which can cause gaming issues. Google or YouTube front-end servers use proxy-like behavior. They terminate TCP connection themselves. How traceroute connects to all these? Your traceroute 192.168.1.1, your NAT router 10.56.0.1 converge CGNAT carrier NAT 161.49.x.x hubs converge routers 142.250 T/142.251 Google backbone. The key real-world facts, you are likely behind CGNAT. This hub 10.56.01 is a private ISP address, not yours, meaning converge NAT's your NAT, double NAT. This affect gaming, peer-to-peer, VoIP, PMTU behavior, UDP traffic reliability. Your trace route shows IPv4, not IPv6. Everything is IPv4. No IPv6 addresses, no IPv6.google.com hubs, no asterisk notation. So your MTU 1500 IPv4, not 1280 IPv6. But if Converge or Google tunnels or encapsulates traffic, MTU can shrink. Gaming packets may be capped. So what is happening to you in real life? So here's the real world chain with your ISP. Your PC makes TCP or UDP connection to your home router NATs, hit, then converge NATs again, CG NAT. ISP routers apply firewall rules, shaping and possibly lower MTU. Then Google Edge server receive the traffic. This is real world stock effects. So topic packet MTU, what's real world behavior? Routers limit packet size. Kernel adjusts PMTU, which is the kernel of your PC or your laptop. Games or VoIP uses less than or equal 1 to 100 bytes. So the kernel actually adopt the request, not the app code. TCP topic TCP MSS reduction happens automatically after ICMP packet too big. Topic UDP packet design. Apps pre-create small packets 512 to 1200 bytes because PMTU varies. Packet filter firewall runs on every router hop in your trace route. Proxy firewall used by big services like Google determine TCP before passing to backend. CGNAT, you have it 10.56.0.1 hop. IPv6, you are not using IPv6, we are using IPv4. So why this matters for gaming or YouTube connection stability? Because of double NAT. Possible PMTU limits inside Converge. Router firewalls rate limiting ICMP. Example, if ICMP packet too big is blocked, PMTU breaks, your TCP stalls, feels like lag. UDP games avoid this by sending small packets already. This is exactly why you feel difference between ISPs. If you so that's the reason why it feels the connection is different between ISPs, whether PLDT or Converge. So does the Converge use the same port like 40021 for everyone? No. But yes, Converge reuses ports heavily because you are behind CG NAT, carrier grade NAT or SP NAT. What you get, a private IP like 10.x.x.x or 100.x.x.x on your router's one side. Converge CGNAT translates your traffic to a shared public IP. The CGNAT assigns a random port per flow called a NAT binding. Those ports are not unique to you. Thousands of subscribers can share the same public IP, each with overlapping port ranges. When the NAT binding expires, the port can be reused for another customer. So no, fix 40021 for all requests, but heavy port recycling happens inside their CGNAT. Second, why is TCP or IP still discussing NAT? Isn't that old? It's old but extremely relevant today because IPv4 is still dominant. The world didn't fully move to IPv6, so NAT is still needed to share addresses. CGNAT is now everywhere. Your Converge plan uses CGNAT. Most Asian ISPs use CGNAT now. Modern apps, Zoom, games, VoIP, WebRTC must work through NAT. So NAT traversal, stand, turn, ice, hole punching is an every modern communication system. Cloud gaming, P2P, mobile carriers all rely on NAT tricks. NAT traversal is more important now than 15 years ago. How NAT editors relate to real-world use. So the book says NAT editors rewrite payloads when the application embeds IP or port inside the data. In real-world example, FTP active mode, FTP control channel includes port 192.168.1.5, 30, 121. NAT must rewrite this because it contains private IP and port. pptv/sip/h.323/some games. These protocols embed address inside data payloads. NOT, NOT must edit them. If NOT is done, the call will fail. This is why VoIP calls fails. Games can host lobbies and P2P cannot connect behind CGNOT. This is exactly what happens to many converged users. How this relates to your trace route. Your trace route shows your router 192.168.1.1, then converge internal subnet 10.56.0.1 proof of CGNOT, then converge public IP backbone 161.49.x.x, then Google. This means you private IP to converge CGNOT to public IP internet, and your TCP SYN goes like this: U 192.168.1.x colon local port to home NAT become 10.56.x.x colon NAT port to converge CGNOT becomes 161.49.x CGNOT port to Google 142.251.x.x colon 443. This is a two-level NOT. The book refers to this exact situation. Complications arise when multiple NOTs exist in the path. This is literally a real-world setup. So NOT traversal, stun, turn, hole punching is what modern app use. Any app that must allow incoming connections uses stun to discover your external address, like WebRTC Zoom, turn, when direct connection is impossible behind CGNAT, ICE, framework that tries every FAT, host candidate, reflexive candidate, stun, relayed candidate, turn. This is why Discord connects relay sometimes. Zoom shows UDP block. Games show strict NAT type. Your converged CGNAT is the reason. Summary: how everything fits together. NAT editors needed by protocols that embed addresses, otherwise things break. SPNAT or CGNAT converge. Uses this. You share one public IP with many users. So these NAT are used for SPNAT or CGNAT converge, low-end converge uses this. You share one public IP with many users. NAT traversal, your app uses stun or turn to work through CGNAT. Hole punching, used by games and P2P, often fails behind CGNAT. Multiple NAT layers, you have two NATs, home plus CGNAT, harder for apps. Ports, recycled and not unique to one subscriber. So why NAT traversal exist? The root problem. NAT breaks end-to-end connectivity. Specifically, a device behind NAT cannot accept incoming connections because its internal IP 192.168.x.x/10.x.x is not routable. The NAT only knows how to send packets outwards. It only creates a NAT binding after you send a packet outward, the SYN or UDP packet. This means if a remote peer tries to contact you first, the NAT has no mapping, packet drop. This is why P2P cannot connect. Hosting game lobbies breaks, voice or video fails, WebRTC needs stun or turn or ICE. Now let's anchor this to the TCP SYN story. How the TCP SYN flow works through NAT. Let's say your device sends 192.168.1.10 colon 5000 to SYN to that SYN to 64.233.161.100 colon 443. Your home router NAT rewrites it to something like 100.120.50.33 colon 43010 SYN packet to 64.233.161.100 colon 443. Then converge CGNAT rewrites it a second time, 161.49.12.7 colon 59202 to SYN packet to 64.233.161.100 colon 433. This creates two NAT bindings. Home NAT 5000 to 43010, CGNAT 430259202. Now the remote server replies 64.233.161.100 colon 433 to SYN/ACK to 161.49.12.7 colon 59202. CGNAT matches 59202 sends to 43010. Home NAT matches 43010 sends to 5000. TCP handshake completes. How NAT traversal relates to TCP/C. Now imagine a peer wants to connect to you first instead of outgoing. The peer will set scene to 161.49.12.7 colon 59202 but converge CGNAT says I have no mapping for 59202 initiated by this internal route user. So packet is dropped. Thus, TCP P2P cannot work behind CGNAT unless hole punching succeed or the NAT traversal works. Why UDP is used for NAT traversal? TCP can be punched, so the hole punching can work in TCP. The only protocol that can do this is UDP. So SYN requires existing NAT mapping. UDP is much simpler. No handshake NAT mapping is created when you send any UDP packet. Hole punching works with symmetric openings. This is why WebRTC, Discord, Zoom, Games, Fortnite, COD, Apex, Valorant, etc. all rely on UDP for NAT traversal. How STAN works connected to NAT plus SYN. STAN is UDP based. Your device sends a packet 192.168.1.10 colon 54321 to UDP to STAN server colon 3478. NAT rewrites twice. CGNAT colon 161.49.12.7 colon 60211. The STAN server simply replies, your public or IP port is 161.49.12.7 colon 60211. This is your reflexive candidate. This is how Discord or WebRTC knows what your public address is. But in CGNAT, this is not really your IP. It is the CGNAT's external mapping. How UDP hole punching works. Two peer behind NAT try to connect directly. Both send outbound UDP packets to each other. This forces the NATs to open temporary pinhole mappings. Internal to NAT port A to CGNAT port B. If both NATs preserve port predictably, hole punching succeeds, but CGNAT usually use symmetric NAT, random port mapping, no endpoint independent filtering. Thus, hole punching usually fails on convert CGNAT. That is why you get NAT type strict can't host lobbies using relay server connecting through turn, and that's why you're using NAT traversal via UDP. What ICE does, final integration. ICE tries 3 connectivity paths in order. Host candidate, your local IP 192.168 only works on LAN. Reflexive candidate from STAN, your CGNAT address 161.49.12.7 colon 60211. This is where hole punching attempts happen. Relayed candidate turn, if hole punching fails, then turn server relays all packets, U to turn to peer. So you may need to contact some other server that is related to your host. Now this increases latencies but guarantees connectivity. This is exactly why Discord sometimes says RTC connected via relay. Zoom says UDP block using TCP mode. Games show NAT type strict. Your converge CGNAT forces many apps to use turn or relay. How this connects to PMTUD and fragmentation. Inside STAN or ICE or hole punching, multiple UDP packets are exchanged. Some large packets, SDP, DTLS, handshake, may exceed MTU. PMTUD or PLPMTUD reduces packet size. Games and real-time apps force packet size to 1 to 100 bytes max to avoid fragmentation, because fragmentation breaks hole punching, breaks NAT mapping, often fails at CGNAT layers, increases latency, causes packet loss, so UDP-based apps intentionally keep packet size small, 1 to 100 bytes. Bringing it all together, here's the whole flow in a real game, like Valorant, Fortnite, COD on Converge CGNAT. Game starts, your game sends UDP packets outward to servers, NAT creates mapping. Game needs P2P or lobby connectivity. It sends STAN request, get CGNAT external IP or port. Third, game tries hole punching, often fails because CGNAT is symmetric. Fourth, ICE falls back to turn or relay. Game displays NAT type strict, can't host lobbies connected via relay. FIP MTU is reduced because CGNAT plus VPN-like turn tunnels requires smaller packets, apps lower packets to 1 to 100 bytes. TCP SYN is only used to set up control channels, but real-time UDP carries audio or video or game updates. CGNAT ensures no incoming TCP SYN ever reaches you. Thus, unless hole punching works, you cannot receive inbound connections. So how does your device know to use UDP instead of TCP for STAN? Because the app decides this, not the OS. Example, WebRTC browser, Discord, Zoom, Games, Fortnite, Valorant, COD, LiveKit, SDK, mobile apps. All of them explicitly implement STAN using the UDP because UDP can create NAT mappings without handshake. TCP cannot be hole punch. SYN requires existing NAT mapping, so the WebRTC stock or LiveKit client SDK says use UDP to send a STAN binding request. No TCP is ever used for STAN in real-world WebRTC. How is STAN used in real world today? STAN is used in every voice or video or data P2P system. Apps using STAN in the Philippines: Zoom, used for P2P fallback and candidate gathering; Google Meet, WebRTC STAN; Messenger calls, WebRTC; Discord or voice audio, ICE plus STAN plus turn; Valorant or Fortnite or COD; UDP NAT hole punching; WebRTC apps like Kit, Janos, MediaSoup, Connectivity; mobile games, MLBB, CODM, matchmaking plus P2P hole punching. So STAN is part of daily life of every Converge subscriber. How WebRTC uses STAN or turn or ICE? WebRTC is a framework that handles NAT traversal. The browser or mobile SDK does the following automatically. Step 1. Host candidate, your local address: 192.168.1.7, 53502. Only works if both peers are on the same Wi-Fi. Step 2. Reflexive candidate STAN. Browser sends UDP to stan.1.google.com :19302. STAN server replies 161.49.x.x :60210. Your device learns my public address via CGNAT is 161.49.x.x :60210. This is where hole punching attempts to happen. Step 3. Relayed candidate turn. If hole punching fails because CGNAT is symmetric, this is converged. Peer also behind CGNAT. UDP block. Then WebRTC uses turns. U to turn server to peer. This is the relay mode. Where does the pinhole happen in real world? A pinhole is a NAT mapping created by sending any outgoing UDP packet. Real world examples in Converge: Volapcan that fail pinhole, app, Discord voice or video, symptom, RTC connecting to using relay, Y, STAN fails to turn fallback, Zoom, symptom, UDP block using TCP mode, Y, CGNAT symmetric, Valorant, NAT type strict, Y, hole punching fails, Call of Duty, unable to connect to host, Y, cannot receive incoming packets, Fortnite, voice chat using relay, Y, direct path impossible, LightKit on mobile data, peer connection uses turn, Y, CGNAT. So yes, these failures really happen constantly in Converge CGNAT network. Why turn causes lower MTU 1 to 100 bytes? Because turn behaves like a VPN tunnel. Your packets to turn server to peer. These create UDP encapsulation, possibly DTLS encryption, WebRTC framing, turn framing. To avoid fragmentation, WebRTC reduces packet size to 1 to 100 bytes. This is exactly connected to your earlier PMTUD or fragmentation lessons. How this connects to a NAT TCP sync flow. So let's merge the concept. TCP SYN flow, three-way handshake, can be hole punch. CGNAT blocks unsolicited SYN. Thus, TCP P2P is impossible behind CGNAT. UDP stun flow sends an outbound UDP, then creates pinhole. NOT lines the mapping, reflexive candidate discover. ICE attempts. It try host candidate LAN, then or try reflexive candidate stun, then try relay candidate turn. With converge CGNAT, reflexive candidate almost always fails. Symmetrically mapped relay candidate is used. Turn. Everything is logically consistent. How WebRTC firewall logic works inside browser? Every browser has a WebRTC stack that uses ICE, parses stun or turn server list, generates candidates, handles NAT traversal, manages DTLS to SRTP encryption, negotiates connection. There's no operating system firewall rule. WebRTC bypasses not using stun or turn, not OS firewalls. How it connects to your LiveKit plus Next.js plus React app. LiveKit is built on WebRTC, so everything above directly applies. Here's what your LiveKit client does automatically. First, collect host candidates, your device IP inside the LAN. Second, stun request, LiveKit default stun servers, stan:1.google.com:19302. Third, gets reflexive candidates, your CGNAT external address. Fourth, sends connectivity checks, trial hole punching. Fifth, if fails, it fall back to turn. LiveKit uses its turn server. Turn your livekit server 3478. All media audio or video is relayed. This is why latency increases, bitrate decreases, packet shrinks to 1 to 100 bytes. If you were wondering why LiveKit feels slightly slower, because Converge CGNAT forces you through turn. Your Next.js front end only controls signaling. All the NAT traversal happens inside the browser. WebRTC stuck, not in your code. So summary, full connection graph. Your LiveKit React app, which connect to JS, JavaScript, WebRTC API, connect to browser, WebRTC engine, to ICE gathering, host candidate LAN, reflexive candidate stun, relayed candidate turn, to connectivity checks, to hole punching, fails to turn, then LiveKit SFU relays all streams. Everything your app does is abstracted because the browser does WebRTC automatically. If you want, so what real world networking, what actually gets used? 80 or 20 rule. 80% of modern real-time apps use UDP plus STAN plus ICE. It fall back to turn if CGNAT blocks direct UDP. So this is applicable to all the real-time apps like video calls, any real-time apps like Discord, games, etc. So 20% of corner cases, TCP fallbacks like Zoom TCP mode, WebRTC turn/TCP. So the TCP are just fallback in real-time apps. They mostly use UDP plus STAN plus ICE. So they use hole punching, STAN, ICE, etc. PMTU UD adjustments, lowering MTU to 1200 for relay paths. So the adjustments, just like the fragmentation, is rare with the previous fragmentation chapter or the IP header chapter. It's also rare for NATs, for falling back on this or TCP turn over TCP, WebRTC turn over TCP, and chopping the fragments. It's also rare for them to do that. So that's the 20% corner cases. So STAN is still heavy used today, used by WebRTC, Chrome, Safari, Firefox, Discord, Zoom, Google Meet, LiveKit, almost all games that use peer-to-peer networking. Turn is used when STAN plus HCP hole punching fails. Turn usage is rising because of CGNAT like Converge, breaking direct connections, and IPv4 exhaustion. TCP sync only applies to TCP connections. WebRTC media never uses TCP unless forced. Diagram home device to home NAT to Converge CGNAT to stan/turn to peer. Now your device will send UDP 23478 stan request to home router, not UDP map port random. So it will connect that to that random port. Then it will contact CGNAT public shared IP plus new random port. Then it will connect stan server. Response, your public IP is equal 161.49.x.x:60211. Then it will contact ICE agent in browser, and then it has host candidate LAN 192.168.xx server reflexive stan result, hole punching attempts, and then if it fail, relayed candidate turn. Use only if hole punching fails, then remote peer or live kit SFU. So how WebRTC actually works? JS API, native ICE engine. The JavaScript API is thin. Browsers do the heavy lifting. When you write const pc equals new RTC peer connection, argument ICE servers, the browser automatically sends stan request, gather ICE candidates, performs hole punching, falls back to turn, adjusts MTU 1 to 100 bytes typical, chooses the fastest path ICE nomination. JavaScript does not implement stan or turn. Chrome or Firefox or WebKit, C++ networking stock does. Code example, WebRTC stan and turn usage, React or Next.js. Const pc equals to new RTC peer connection, iServer colon, then URLs stan.1.google.com 19302, then URLs turn example.com 3478, username, user credential pass. Then next, pc.on ICE candidate with an equal argument event to if event.candidate. Inside this is console.log ICE candidate, event.candidate. Chrome will automatically generate host candidate to 192.168.1x, SR flicks candidate from stan, relay candidate from turn if needed. Relationship stan to hole punching. Stan is not hole punching. Stan gives your public IP or port mapping. Hole punching uses that public mapping to create symmetric outbound traffic flow. First, device sends stan request to NOT creates outbound mapping. Second, device learns its public mapping from stan. Third, device and peer send UDP packets to each other using this mapping. Fourth, if symmetric NOT or CG NOT blocks it, it will fails. Turn is used. Turn fallback in real world. Examples in PH or Converge Bulacan. These apps frequently fall back to turn because of Converge CGNAT. Zoom shows using relay or TCP. Discord RTCP connected via relay. Google Meet hidden but uses turn. Valorant or COD or GTA V not type strict. LiveKit will switch to turn for many clients. Reason, Converge CGNAT equals symmetric NAT, worse for P2P. ICE candidate types explained clearly. Host candidate 192.168.1.25:58321 works only inside your LAN. Server reflexive stan 161.49.12.7:60211. This is where hole punching happens. So in this server reflexive stan or 161.49.12.7 is where the hole punching happen. If symmetric, CGNAT will fail. Third, relay candidate turn. Turn.example.com 3478 relay address 34.91.12.4 64555. Your media now flows you to turn to LiveKit, high latency but guaranteed. Diagram, TCP SYN versus UDP hole punching. TCP three-way handshake, client to SYN to server, server to SYN/ACK plus to client, then client ACK to server. Connection established, works even with NAT because NAT tracks TCP state, or it works even in CGNAT. So UDP hole punching, no handshake. Client to UDP to STAN opens not binding. Then client sends UDP to peer. So after the client send the UDP to STAN that opens not binding, the client will send UDP to the peer. Then peer will send UDP to the client for them to have direct connection. If both routers allow response to an outbound flow of the peer to the internal, it means success. If CGNAT blocks that because of that layering, it will fail. It will use the turn. PMTUD, path MTU discovery in WebRTC. When packets go through turn, relays, or VPN-like tunnels, MTU becomes smaller, i.e. 1 to 100, because you now have to worry about the tunneling of this turn. Now WebRTC automatically fragment or reduces the payload size. LiveKit and WebRTC handles this automatically. So how LiveKit uses stun or turn? LiveKit server config example, ingress colon, then UDP underscore port underscore range colon argument 2000 comma 3000, then use underscore external underscore turn colon true, then in turn colon we have this key multiple key value affairs enabled colon true, domain colon turn dot example.com, TLS underscore port colon 5349, UDP underscore port colon 3478, user colon turn user, pass colon turn pass. LiveKit behavior: first, browser tries host to STAN candidates. Then second, if direct UDP works, SFU direct. Third, if UDP fails, it will turn to turn/UDP. If UDP completely blocked, turn/TCP. If TCP blocked, it will fall to turn/TLS or 443, port 443. LiveKit plus React/Next.js front end flow. Your React code calls LiveKit client SDK const room equals await.connect argument LiveKit underscore URL comma token. So browser automatically runs ICE, talk to STAN, fallbacks to turn if needed. Your code does not implement networking. WebRTC handles all connectivity. Which protocol is most used? Ranked by real-world usage. First, STAN, 90%, always used for ICE. Second, UDP, first choice for real-time media. Third, turn, increasingly common due to CGNAT. Fourth, TCP SYN, used only for signaling or fallback. Summary: what is truly happening in real world? STAN is absolutely still used today. Hole punching is still attempted. CGNAT breaks hole punching. Turn usage rises. WebRTC JS API is a wrapper. Browsers do the actual networking. Turn ensures connectivity when CGNAT is present. LiveKit internally uses WebRTC, therefore relies on STAN or turn or ICE. TCP SYN is only relevant for signaling and non-media traffic. So not STAN, turn, ICE, and LiveKit diagrams and flowcharts. So this contains 3 pages on a single sheet: packet step-by-step flowchart, full LiveKit deployment diagram, SFU plus turn plus CDN, executive or simplified diagram plus short code excerpt showing WebRTC ICE/STAN usage. A. Packet flowchart: TCP SYN, UDP hole punch, STAN, turn, and ICE step by step. So you emits traffic packet sent to socket TCP or UDP. Then if TCP SYN, TCP handshake triggers NAT mapping on N1, so that's a normal TCP handshake. If UDP no SYN, immediate to send may create NAT mapping on N1, so it will create a mapping as well. Does the app use NAT traversal, so like WebRTC or P2P? So again, web traversal are only for those real-time apps. So if you're calling a video call, if yes, it will perform ICE gathering for this for its code in this LiveKit code. So the packet will perform ICE gathering. ICE gather candidates. It hosts candidate local IP port. So the candidates is the first threshold, the local IP, and then server reflexive candidates done to not public IP port. So the server reflexive candidate will be your NAT or converged public IP and port. Relayed candidate turn allocated relay IP or port in case the hole punching did not work. So no, for no, normal NAT routing, remote server, HTTP server done. So for normal TCP connection, which is 80% of the internet, or 90, is it's done. But if you're using real time, this is what happened. Connectivity checks, stan binding, UDP attempts. Try different host. Try direct host like Hostlan. If it didn't work, try reflexive hole punching between NATs using exchange reflexive. Each side address. Each side sends packets to the other reflexive address. NAT hole may be opened. If checks succeed, peer-to-peer UDP path established. If all fail, fall back to turn relayed path. Then, when turn used, client sends UDP or TCP to turn server. But usually, UDP is preferred. Turn relays between. So, when the turn is now turned, the client will be triggered to send another packet, a UDP packet. Now, turn relays between clients, increasing latency plus possible MTU shrinkage. Then it will establish path use for media, SRTP, or data. Notes inline in the canvas shows exact path. Example scene packet format stan, binding request format, turn allocate or send indication, and depicts where TCP scene is relevant only for TCP flows, while UDP hole punching is stan based. Full LiveKit deployment, diagram detailed. So for clients, browser or mobile, it will connect to WebSocket, HTTPS signaling to LiveKit REST and real time to LiveKit room service SFU, and it will handles or tracks rooms. It will does SFU uplink slash downlink. So what are SFU? So then the client will simultaneously send to media, local NAT, and LiveKit as well, media via WebRTC. So the local NAT will connect to optional turn pull for clients behind CGNAT or strict firewalls. Then LiveKit will connect recording. Oh my god. Will connect to record or local net, and then it will connect to transcoding, which is optional. So the turn server, as you can see, is in the LiveKit room service. So turn server co-located or external. Relays media when P2P fails. Public IP needed. It supports UDP, TCP, or TLS. And there's also in WebSocket in HTTPS, there's an optional CDN or static content, JS SDK assets. Operational notes inside documents. So how to configure legend signaling HTTP or WebSocket to LiveKit control pane, media, WebRTC, DTLS plus SRTP, turn, release media when ICE fails, CDN for distributing large static asset or recorded files. So those are the assets that you want to load fast to the clients. Operational notes inside documents, how to configure turn credentials for LiveKit, short snippet of config, how to point WebRTC clients to stun and turn servers via RTC peer connection iServer. So also included recommended sizing, turn servers per 1000 concurrent peers, TLS requirement, and relayed bandwidth cost. Note, so this turn server, there's a limit. That's why there's a limit in LiveKit of 100 concurrent users. So in executive explanation, summary, problem, home or ISP CGNAT prevents direct incoming connection. Solution, app tries like easy or fast path first, like direct UDP, fallback to relays, turn if needed. Stand role discovers what public address you're not exposed. Server reflexive. So the role of stun is to find what the actual address along the way, or the called server reflexive, to be able to use that first before that turn. ICE role, coordinator that tries all candidate paths and chooses the best working one. Turn role guarantees connectivity by relaying when direct connectivity fails, cost bandwidth, and adds latency. LiveKit orchestration plus SFU for media uses stun or turn or ICE under the hood. CDN used for static or recorded assets. Appendix, short WebRTC snippet, what the browser runs. Const PC equal new RTC peer connection. Then iServers colon, then URLs colon stun.1.google.com colon 19303, URLs colon turn dot example.com colon 3478 colon username colon user credential pass. So the canvas also contains annotated packet example, TCP SYN handshake versus UDP stun binding request or response, TLV layout, turn allocate or permission / send flow. Does the TCP SYN only apply to TCP? Yes, SYN is part of TCP three-way handshake and only for TCP sessions. UDP has no SYN. NOT mapping for UDP are created by sending packets and seeing how the NOT maps source IP port. Is TCP still prevalent? Yes, most web traffic, HTTP or HTTPS, historically runs over TCP. Newer web transport, QUIC, runs over UDP and is increasingly used for HTTP over 3. Both TCP and UDP are widely used in the real world. WebRTCP media typically uses UDP but can fall back to TCP or TLS. Why does turn or reduce effective MTU and increase latency? Turns relays add extra headers or encapsulation and another hop, client to turn to peer. That increases per packet overhead. So apps often shrink payloads to 1/200 bytes to avoid fragmentation and raises round trip time because of extra relay hub. What is ICE? ICE is the orchestration. It gathers candidate, host, reflexive via stun, relay via turn, and performs connectivity checks. Stun binding exchanges. It picks the best working path, P2P UDP if possible, otherwise turn relay. How WebRTCP and stun relate to LiveKit or your app? Your browser or LiveKit SDK will create an RTC peer connection with ICE servers, stun in turn. The browser runs ICE automatically, gathering, checking. LiveKit orchestrates rooms or SFU and accepts stun or turn config so clients can connect reliably behind CGNATs like Converge. Why apps often use stun? Stun is lightweight, widely supported, and enables hole punching in many NAT types. It's the 80% solution for P2P connectivity. Turn is the fallback when stun-based role punching fails, like strict CGNAT. Is this what's happening on Converge? Very likely. Your traceroute shows IPv4 hops through Converge for P2P WebRTC. Ups, your public address may be CGNAT nated, which forces stun to reveal a reflexive address, often shared and often causes turn or relay usage.